We've talked about other distributions. We talked about a binomial distribution in the last lecture. In the lecture before that, we talked about probability distributions. When we talked about the probability distribution, we talked specifically at a discrete probability distribution. So we're going to look at a probability distribution again, but this time we're going to talk about a continuous probability distribution, and specifically the normal distribution. Okay, so let's take a look. So a normal distribution is a type of continuous probability distribution. Something to remember is that discrete is when we talked about data, right? When we talked about discrete data or discrete random variables, we talked about the fact that these are something that you can count. Continuous is something that can't necessarily be counted. So we're not really creating a histogram from this because we can't count 1, 2, 3, 4, okay? But continuous can be put on a number line. So that's what we're looking at. So we can still look at these graphs of normal distributions. So let's write some of this down. So a normal distribution is a continuous probability distribution. So again, we talked about discrete. This is specifically continuous. Remember, continuous says can be put on a number line, but not necessarily an integer. When we graph it, because that's what we're going to be concentrating on. We're not going to be concentrating on the frequency distributions or the probability distribution in the table. We're going to be looking at the graph, this normal graph. So we talked about things being skewed left or skewed right. The graph of the normal distribution is perfectly symmetrical.
We're Brad and Haley Devine.
And we're asking you to please stay indoors, stay healthy.
To stop the spread of COVID-19.
Okay. This graph of the normal distribution is called the normal graph. So there are 5 things to look at in particular, and then we'll show you what these curves look like, something that you're actually really familiar with if you've been watching the news or reading the newspaper. So the first thing is, because it's perfectly symmetrical, the mean is equal to the median, and actually that's all equal to the mode as well. So that's the first thing. So if you remember, skewed right skewed right means if something is skewed right, then the mean is greater than the median. no skew because the mean is equal to the median. So that's the first thing. The second thing is that it's symmetrical about the mean. So we say the normal curve, the normal graph, or sometimes the normal curve. So when we say it's symmetrical, the mean, median, and mode are in the center. Area under the curve is equal to 1. So we talked about this with the probability distribution as well, that if you, with the discrete probability distribution, that if you take the sum of all of the probabilities, it's equal to 1. Well, the same thing is true here. If you take the sum of your probabilities, you get 1, and that sum is the area under the curve. So the total area under the normal curve is equal to 1. The next thing is that the normal curve will approach but never touch our x-axis. And once we see a picture of the normal curve, then this will make more sense. In other words, what we're saying is that the probability of an event is always greater than 0. It may not be much greater than 0, but it's a little bit greater than 0. Okay, and we'll have outliers, okay, but there's not really an outlier that's impassable. And then the last thing, which isn't going to make a lot of sense right now, I'm going to write it down and then we'll explain it when we see an actual normal graph. So the last thing is that it's centered about the mean and it's based on standard deviation. So if you start at the mean and you go 1 standard deviation to the left and 1 standard deviation to the right, which is the exact center of the graph, then the graph is going to curve down. But to the left of those points and to the right of those points, okay, then the graph is going to curve up. So I'm going to write that and then I'm going to show it to you. So remember, mu is the mean. So this is saying 1 standard deviation to the left of the mean. And this is saying 1 standard deviation to the right of the mean. And then to the left of u minus theta, sigma, in other words, to the left of the mean minus 1 standard deviation, and to the right of the mean plus 1 standard deviation, our graph curves up. The inflection of the graph is changing. The curve of the graph is changing. So I'm going to write that here too. Desmos. I don't know if any of you have heard of it from your other math classes, but it is a graphing calculator, and I'm going to show you what it looks like so that it's nice and accurate. But for right now, I just want to give you some idea. So we have our x and our y-axis. And our curve, if, like I said, you've seen this a lot, paying attention. If you've been paying attention to the news and you've been looking at all about the number of hospitalizations for the coronavirus, and you can see we're talking about, okay, the number of hospitalizations increases, and then it reaches an apex, and then it comes back down again. This is what our normal curve is, okay? We reach this apex at the top, and then it comes back down, and it comes back down in a way that's symmetrical, okay? So it looks like this, approximately. Okay, so you can see here, this is not perfectly symmetrical. It does look better on my paper, though.
Please help stop the spread of COVID-19.
But this over here, this peak, this is our mean. Okay, and you can see here that there are 2 points where it's going up, and then it kind of starts to change. And when it starts to change, okay, what we're saying is from here to here, it's going down. So in other words, we're talking probably about points around here. And this point would be 1 standard deviation to the left of the mean. And this would be 1 standard deviation to the right of the mean. So these would be called your inflection points. So this is your normal curve. This is what it looks like, approximately. I'm just going to put in here, this is not really relevant to you, but I'm putting in here just a note for the board notes. That we use Desmos.com. So Desmos.com is a website to show graphs of the normal distribution. Just for people looking at the board notes, this might be helpful. And the way that you would graph it is you would type in EIS, and then the mean and the standard deviation. So for right now, that doesn't mean very much to you, but somebody who's doing board notes, who's only looking at board notes, this might be helpful. Okay, so let's take a look at the normal distribution. Okay, let's make this a little bit larger. So you can see here that we're calling 0 the mean, okay? And when we fill in the mean, what we can do is, and what you'll see with the normal curve, is that we don't have to fill in the actual mean. What we're gonna do is we're gonna use 0 to represent the mean, okay? And then we have standard deviations away from our mean, okay? So this is saying that the standard deviation away from the mean is 0.2, okay? So if we go to 0.2, we're going here to 0.2. And this is where our curve sort of changes, where between negative 0.2 and 0.2, we're talking about it moving down, but then over here, as we move to the right, it's kind of, now the shape of the curve changes just a little bit, okay? These would be called inflection points. So don't worry so much about, well, can I see the shape changing, or how different does it look? Don't worry about that. I want you to just understand that the shape does change a little bit, okay? We're going from, okay, we're going up, up, up. And then at this point, we're kind of changing the way that we're looking at it. And we're saying, okay, well, our curve is now curving. This is sort of where it stops going up, 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 up. And it starts to curve and turn around, okay? So think of it like the flattening of the curve. Again, if you've been following the news, this is where we say, okay, well, we want our curve to flatten. So where is the apex? This is where we're sort of saying, where's the apex, the highest point? Are we getting closer? And this is the point where we're saying, oh yeah, we can see that now we're making a turn and we're starting to reach that apex right here. This is saying, okay, well, we're starting to change, and instead of just going up, 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 we can see that we're starting to reach that top, and we're nearing the apex, okay? And then we're coming back down, 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 down. We're still kind of at the top of the curve, and then right around here, we start changing shape again, and we know that we're gonna start going down much faster, okay? So this is the example of the curve. When we talk about the area under the curve being 1, what we're doing is we're saying if we add up, think of creating like little rectangles under here. And if we were to create little rectangles under here and take the areas of all of these rectangles, we're going to wind up with something that's equal to 1. Okay, so that's what we're kind of saying here, is that the area under our curve is equal to 1. Okay, and this is perfectly symmetrical. What's happening on the left is exactly the same thing that's happening on the right, okay? We said it approaches the x-axis, but it never reaches the x-axis. So you can kind of see that here, that even over here, we can still see the red line, and over here, we could still see the red line, because there's just a little bit of area, a little bit of space between that curve and the x-axis, where we would say, okay, well, the amount of data there is 0. Okay, and we're saying, no, that's never actually the case. We could have these outliers, okay? And that's what's going on here. Let's take one more thing here. So I'm gonna take, so here's another example of a normal curve. So the A, the first number, is our mean, Okay, so I created this so that it would be a graph that you could easily see here. So don't worry so much about the numbers. What I want you to notice is what happens with the mean. As the mean changes, the location of this graph changes. Okay, the height doesn't change, the width doesn't change. It's just the location that changes. That's the only thing that the mean does. Whereas if we change the standard deviation, that's what the second number is. If we change the standard deviation, that changes everything, okay? So our standard deviation, it changes, as we change the standard deviation, the width changes, but also the height changes. So we talked about like flattening the curve, right? When we talk about the coronavirus, this is what we mean when we say flattening the curve. We're saying we want this highest point to be as low as possible, okay? And we also talked about the spread of the data, right? What does the apex look like? Is the number of hospitalizations going to increase, and then all of a sudden it's going to come down very, very quickly? Okay, meaning, is this over within 6 weeks? You know, did we go up in the first, let's say in the last 3 weeks, we went up very, very quickly, and now we're going to come down very, very quickly, where the number of hospitalizations decreases very quickly? Or is it going to be more like this, this is what it looks like, more like this, where we increase the number of hospitalizations, we don't really reach as high a point as we thought, okay? So you can see the difference between like this normal curve, where we're reaching a much, much higher point, okay? But it's taking a little bit longer to come back down, okay? So we're kind of flat at the top, where the number of hospitalizations kind of stays the same for a little while, and then we come back down. And that's sort of what we've been seeing more over the last few weeks, and why people are more concerned that this is going to take longer, because essentially what we're doing is we're saying, okay, it goes up, and then it flattens at the top, and then it goes down. So what this flattening at the top is, it's also extending the time that this takes, right? So instead of here, this time may look like, if we look at this red graph, this time may look like 4 weeks or 6 weeks, whereas this one, maybe it's more like 8 weeks or 10 weeks or even 12 weeks, where it takes a little bit longer, okay? And again, the area under this curve would also be 1. So as it flattens, as the apex comes down, it widens. And that's why this has to happen, is because that area has to remain the same. And if it didn't get wider as the apex comes down, okay, if it didn't get wider, then the area would no longer equal 1. We're trying to keep that area equal to 1 because that's what a normal distribution is, okay? So think of a rectangle. If we take a rectangle and we decrease its width, then in order for the area to remain the same, the length has to increase, okay? So this is the same idea. This is our normal curve, okay? Okay, so let's talk about this a little bit more. So let's say what we're going to concentrate on in this one is the way in which we draw this normal curve. So I'm going to redraw it, okay, in our notes. And instead of talking about it as an actual number for the mean, we're going to label our x-axis in terms of standard deviations away from the mean. So you can see here that we have our mean. And instead of saying, okay, well, our mean is 2, or our mean is 200, or 300, or 400, we're not going to label our mean as that number. We're going to label our mean as, on the x-axis, 0, okay? So let's go back to our notes, and we'll do a comparison, okay? So let's say, for example, just a comparison in the way that it's labeled. let's say that so let's talk about the way that we label the normal curve. So we can label the normal curve with the actual mean and with our numbers, like we do with the other probability distributions, right? Hello? Okay, so let's talk a second about, let's take an example, okay? So let's say, again, this is just two different ways of labeling the normal curve. Let's say that we're talking about the scores on a New York State grade 4 test. Okay, like some of you, most of you have grown up in New York State. Well, probably a large majority of you, but for those of you who don't know, every year you take a state test starting in grade 3. So, and it's uniform across New York. So we're talking about the scores on this New York State test. And let's say that they're normally distributed. Okay, they're not always going to be normally distributed, but let's say that they are. Okay.
Just giggling with people. Look how tall you are.
And let's say that the mean test score is 305 and the standard deviation is 40. So I'm actually not even going to label a y. And the reason why I'm not going to label a y-axis, okay, meaning our vertical axis here, the reason why I'm not going to label that is because it's kind of irrelevant to us how many students there are, okay? What the normal curve will do is it'll give us this shape. It'll tell us what the shape is. We don't need actually, we don't need to know the height. So let me just clarify something because I'm not sure if it was clear in my explanation. When we talk about the mean is exactly the center. It's what's on the x-axis. The y-axis, remember, is the height. That's the number of people at the mean. So when we were talking about, when I mentioned the virus, right? Let's get rid of one of these. Let's take this one, okay? This here would be our mean, okay? And if you remember, I said if we change this, what we're doing is we're changing location, okay? This would be like changing the date, but the height would be the number of depending upon what we're counting. So we were talking about hospitalizations. So the height is the number of people hospitalized. So if we want to change or flatten the curve, what we're doing is we're saying, let's decrease the number of hospitalizations. That's what flattens the curve, okay? That's why we say, okay, the standard deviation is changing. That's changing the spread, okay? But what's actually flattening the curve is like the number of hospitalizations. How high does this go? So the mean isn't changing, okay? The mean here isn't changing right now. What's changing here is the number of hospitalizations. When they say flatten the curve, they're saying, okay, we're flattening the curve. It's increasing over a smaller amount of, over a larger amount of time or something. But the number of people hospitalized is decreasing.
So much time at now, where she's literally getting her life saved every day that she's here. You know, she lights up when she comes here. That's not the norm in a lot of places, especially a hospital.
Without this place called St. Jude, none of this would have been possible.
Okay, so let's graph this, okay? So if we graph it again, we don't really care about the height. What we're doing is we're just showing you how it's being labeled, okay? So what we're doing here is we're saying the mean, which is the center, is at 305. Now, the way that the curve is going to change is we're going to go 40 to the left and 40 to the right. So 40 to the left is 275. And 40 to the right, 265. And 40 to the right, which would be at the same height as 40 to the left, is going to be 345. So these heights are the same. We know that because it's symmetrical. So if we're 40 to the left, it's going to be the same as 40 to the right. And then this is kind of where we talk about our inflection points. And then here, now we're turning around and we're starting to change the shape of the graph. Okay. So this would be our one way to label our normal curve, where the center is the mean, and then we go whatever number is this one standard deviation to the left, and whatever number is one standard deviation to the right. Now there's another way to label this. We don't have to label it like this. The standard normal curve, meaning what the curve looks like no matter what, okay, is that the center we would just label as mu or 0. This would be one standard deviation above. This would be one standard deviation below. And now here's our normal curve, okay? So we don't have to label it with actual numbers. What we're doing is we're labeling it as 0 for the mean. So in other words, this is 0 standard deviations from the mean. That's why we say 0. And then this is one standard deviation above. That's why it's positive. And this is one standard deviation below. That's why it's negative. And we would label it just as like a 1 and a -1. Okay, and I'm going to do this again in bigger. Okay, and what we call this is the standard normal curve. And the reason why I mention this is because there are a lot of things that are uniform to every single curve, okay? For example, the percentage of the area under the curve is the same between one standard deviation below and one standard deviation above. So in other words, no matter what our curve looks like, the area, the amount of curve under here is the same, the percentage of the curve. That's always the same, regardless of how wide. It's the same as up here too. Okay, regardless of how high this curve goes, regardless of the standard deviation, this always remains the same. Okay, so let's do this nice and large. Okay. And I'm going to do the best that I can. Let me do it in black. Okay, so the center is labeled as 0. these numbers is the number of standard deviations away from the mean. So if we were being very specific to a certain situation, then this would just be whatever number the mean is. Just like over here, we said that it was 305, right? Here we're just labeling it 0 because we're saying this is what the mean is. And the reason why we're doing this is we're trying to show what is true about every single normal curve, okay? So we call it the standard normal curve because this is true about every normal curve. It's independent of what the mean is. It's independent of what the standard deviation is. What we're about to talk about is things that are the same regardless of what these numbers are, okay? So that's why we're labeling it very generically. So then the next piece, we can go even just, usually we tend to go up and down by half standard deviations. So this would be 0.5. This would be 1. Maybe 1.5. 2. 2.5. 3. And we can even go up as high as 3.5. And just to be clear, I'll put this here again. This is 3.5 standard deviations above the mean. Okay, so if we go back to this graph here, what this is doing is it's saying, okay, that point where we said 3.5 is if we went up by 40, then we went up by 40 again, then we went up by 40 again, and then we only went up by 20 because we're only talking about 3.5. So we took 40, we multiplied by 3.5, okay, which is 140, and we went 140 away from 305, okay, which is 445. So this is saying what we would be doing is we would be saying, okay, well, this is the height of the curve at that point is the number of people who got 445 on this particular New York State test. Okay, so we can show this on a graph using numbers, but we don't have to. Everything that we're talking about has to do with standard deviations. Okay, because again, we're trying to be independent of those actual numbers, because these are things that are true of every single graph. Okay, now we can go the other way. So here, this would be labeled negative 0.5 because we're a half standard deviation below. So positive and negative has to do with direction. So negative means that we're below, positive means that we're above. And we're going to do the same thing. We're going to go all the way to negative 3.5. Okay, please understand that this looks so much better on the paper than it does on the screen. So I apologize if it looks a little skewed. It is not meant to be skewed. It is meant to look just like this, okay? Where it looks nice and smudged, okay? I noticed this is not quite the same. Let me see if I can change this. So this is more what we're talking about. It looks where, and when I say this is more what we're talking about, I'm talking about where the standard deviations are labeled, okay? So this is how it would be labeled, and this is what it would look like on the graph, okay? So this at 0, this is our highest point. Okay, this is like our apex. Okay, and I'm gonna try and be neat about this. So I'm gonna do this I'm gonna try and show the symmetry of it. Okay. So at negative 0.5, again, this is it's not perfect. But at negative 0.5, we're gonna be at the same height as positive 0.5. Okay. Again, because it's symmetrical. Okay. At negative 1, we're gonna be at the same point as at positive 1. Okay, these here are inflection points. Remember, that's 1 standard deviation. Above the mean. This would also be an inflection point. This is 1 standard deviation below the mean. Okay, so if we wanted to show, if we wanted to tell you what the inflection points were here, it would be this point and this point. Okay, 1 standard deviation above, 1 standard deviation below. Okay. Now we can keep going here. One and a half standard deviations. It's going to be the same on both sides. Then we have 2 standard deviations. Notice it gets a little bit lower. I skipped the 2 here, which is why it looks weird. Sorry about that. Let's fix that. Notice it's getting lower and lower. Then you have 3 getting closer and closer. And then you have 3.5 standard deviations. And notice at this point we're very, very close to the x-axis, to this bottom axis. It's not even, it's not perfect, okay? Meaning we don't touch the x-axis, okay? That's because the number of people who are 3.5 standard deviations away from the mean, or in this case, the number of people who are getting 445 is really, really small, okay? It's really, really small. But it's not 0. In a normal curve, it's not 0. Okay, so let's connect this. So we're going up, 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 up. We're going up, and now at this point, this is where we're starting to say, okay, the shape of our curve is changing. The shape of our curve is now flattening out. It's getting closer and closer to the apex now. And now we turn around, and we're still at the top of the curve. But now what we're doing is we're saying, okay, well now we've come off of the apex and we're starting to decrease. So these inflection points have to do with the shape, okay? So again, your ability to identify them really is, am I 1 standard deviation above the mean or 1 standard deviation below the mean, okay? That's where it's changing, and that has to do with the shape. Okay, so a couple of other things about the standard curve. Okay, the next thing about the standard curve is talking about like the area under the curve. Okay, now if we look at the area under the curve, we said it's a total of 1. These are probabilities. The probability that you will get one of these numbers is 1. Okay, it's a total of 1. But there's a certain percent, right? The closer you are to the mean, the more likely, the more people there are. So let's go back to this one for a second. The greatest number of people are scoring between a 265 and a 345. Okay, that's where the greatest number of people is. They're in that particular range. That's always true. The greatest number of people are within the range of 1 standard deviation. And in fact, it's always the same, okay? Which is why we call it a standard normal curve. So between -1 and 1, 68% of our data falls within this range. 68%. So if you were to shade this, okay, 68% of the data, or 68% of the area, is within these 2 bars. Now, if we take it out further, and we talk about between 2 standard deviations, between here, we have 95% of the data. This is regardless of what the number is. This is why we call it a standard normal curve, because it's always the same regardless of what your mean or your standard deviation is. 95% of your data is within 2 standard deviations. And I'll write this elsewhere so that you can see these numbers clearly, because I realize it's not that clear. Within 3 standard deviations, so from here to here, 99.7% of our data is between that. This is saying that 99.7% of the people are scoring within 3 standard deviations of the mean. Okay? It's kind of like when we talked about outliers. Okay? 445. This is why we call it an outlier, because 445 and 140 below this, so 305 minus 140 is 65. 99.7% of the people are scoring between a 65 and a 445. That's what this is saying, okay? So if somebody scores a 450, that's an outlier. If somebody scores a 60, that's an outlier because they're outside of that 99.7%. So let's write that down somewhere else, okay, underneath. %68 of the data is within 1 standard deviation of the mean. This is, again, it's the same for every normal distribution. It's why we call it normal and why we call it standard. 95% of the data is within 2 standard deviations. And 99.7% is within 3 standard deviations. I just want to add to this. This over here is 3.5 standard deviations. Below the mean. Okay, so the negative means below. Okay, so here's something else that's standard, okay? The area under the curve, or the amount of data that exists below the mean, is 50%. 50% of the data is below the mean, 50% of the data is above the mean. That's what means it's symmetrical, okay? So we'll write that one down too. There are a couple of other properties here. We could look at percentages. What percent of the data is below one standard deviation of below the mean? In other words, how much data falls over here? How much data? We know that 50% falls here, right? We want to know how much falls below, okay, a certain point. So for that, we're going to use z-scores, okay? So remember what a z-score is. A z-score is the number of standard deviations away from the mean. So what a z-score will also tell us, what we can figure out from the z-score, is what percent of data either falls below a certain range, what percent of data falls above a certain point, and what percentage of data falls within, what percentage of data falls below. Okay, so in other words, if I am at some point in my graph, let's say here, I can figure out, because it's the same for every normal curve, I can figure out, well, how much data is below that point. Or I can figure out how much data is above that point. Or I could say how much data is within a certain range. So if we go back to this one again, I can say, okay, what percentage of people scored below 265? What percentage of people scored below a 300? What percentage of people scored above a 300? What percentage of people scored between a 320 and a 420? Okay, so let's sorry about that. So the number of people who scored, I shouldn't say number, I mean percentage. below or above a certain score, or within a certain range. So, for example, let's go back to the testing.
What we do here is go back.
So, New York State test. We said that the mean was 305 and the standard deviation was 40. Okay, so we could ask ourselves, what percentage of people scored below 300? Well, the thing is that a normal curve is the same for everything. So if we could figure out, well, what's the number of standard deviations away from the mean, that is, then we can figure out, well, what's the area under the curve, or what percentage of the curve is below that number, and that will answer our question. Okay, so this seems like it's going to be really complicated, right? How are we supposed to determine area? Where they actually make it very easy for us. So let's start by just figuring out the number of standard deviations that we are. So if you remember from earlier, z-score says take your random variable, subtract your mean, and divide by your standard deviation. The x minus mu tells us the distance from the mean. And then we divide by the number of standard deviations to tell us the standard deviation from the mean. How many standard deviations? So we could do 300 minus 305 and divide by 40. This is our z-score. Okay, so if we do 300 minus 305, okay, we know that that's negative 5. We divide by 40, this tells us we're negative 0.125 standard deviations, okay? So we're 0.125 standard deviations below the mean. Okay, so now the question is, well, how do we figure out the area then? Because it's the same, okay? If we're negative 0.125 standard deviations below the mean, what we're doing is we're saying, okay, well, we're somewhere really, really close, and we want to know the area of the curve under here, okay? Well, fortunately, you don't have to do any calculations. There's this wonderful table. It's called the z-score table. So if we go here, we have our z-score table for us, okay? And let's talk about how to use this, okay? So the row is going to give you your first digit, okay? We need 0.125. So notice this would be like negative 3.4, and then this gives us the next digit. So negative 3.41, negative 3.4, excuse me, negative 3.42. Over here, this would be negative 3.43, negative 3.44, negative 3.45. If we go down here, this is negative 2.5 right here. This is negative 2.51, negative 2.52, negative 2.53, all the way up to negative 2.59, okay? Over here, we have negative 0.1, and this is where we want to be. We want to be at negative 0.125. So notice this goes to the thousandths, okay? So you can round. I'm okay with that. Let's just go with rounding, okay? So you're going to round to the nearest hundredth. So negative 0.125 is the same thing as negative 0.13 if we round to the nearest hundredth. So we round to the nearest hundredth to negative 0.13. So we go to negative 0.1. Okay, that's the 10th. This gives us up to the 10th place. And then we're going to go over to 3. And we get 0.4483. That's the percentage of area that's below the part of the curve that we're at. Okay, so it's about 45% of, a little bit less than 45% of the curve is less than 0.125 standard deviations below the mean. So let's go back. We're just going to say round to the nearest hundredth. So now we're going to go to our z-score table. And this will be posted. Okay. So we're at negative 2.63. So we're going to find negative 2.6. And we're going to go over to the third column. This gives us negative 2.63. So our answer here is 0.0043. And this is essentially saying 0.43% falls less than, at a score that's less than 200. Okay? Okay, let's take another one. What percent of people scored, we'll still do below. Let's say 328. Okay. Well, again, we have to find our z-score. Sometimes the z-score will already be given to you, so you won't have to worry about finding it. But in this case, we have to find it. So we're going to do 328 minus 305 over 40. Notice the only thing that changes is that very first number, that variable. And if we do that on our calculator, we have 328 minus 305. We divide by 40. And we get 0.575. You round to the nearest hundredth, which gives us 0.58. Okay. And now we just go to our z-score table. So here's the thing. We've been looking at below the mean, right? There's a different one for above the mean because it's going to be greater. And you could see that if we're at the mean, right? If it's 0, if our z-score is 0, which means we're at the mean, then the percentage is 50%. It's 0.5, okay? But here we're looking for 0.58. So this is tenths, right? So we're going to go to 0.5, and then we're going to go all the way over. Right here is 0.58. So it's 0.7190. Okay, and just to be clear, this is saying 72% score below 328. Okay, let's take another one. Let's say what percent score above 300? Okay, so this is different. We've been working with below, we want above. So we already found this, but let's just put it in here again. Still need to find the z-score. And here it was negative 0.13. Okay, now here's the thing. The z-score table tells us the percent that falls below. So if we want the percent above, we need the opposite. And we kind of already know this from probability. We know that the total is 1, right? Total is 1. So if we want the opposite, we can just subtract the value that we got on the z-score table. We could subtract that from 1. So in other words, if we go back, we found that number to be 0.4483. So we're going to do 1 minus 0.4483. What we're saying is if almost 45% score score below a 300, then a little over 55% are going to score above 300. Almost 45% score below 300, then a little more than 55% score above 300. So let's do one more like this. Let's say what percent score above 360. Okay, so we need our z-score. This tells us where we are on the normal curve. So 360 minus 305, and then we divide by 40. This tells us we're 1.38 standard deviations. Okay, 1.38 standard deviations. So what we need to do is we need to go to our z-score table. We're in the positives, so we're in the right place. Okay, make sure that you're careful because anything that's negative is going to be less than 50%. Anything that's positive, you can see goes more than 50%. Okay, so 1.38, we go to the 1.3. That's the whole number in the tens place. Then we're going to go all the way to the 8. And we get 0.9162. So we need 1 minus 0.9162. Okay, so the 0.9162 came from the table, but then we need to subtract from 1 because we want what's above. And we get that it's only about 8%. And then let's take another one. Let's say that we want to know what percentage score between 200 and 320. Well, this is a little bit different because we are only getting z-scores, we're only getting percentages below. So in other words, if we just kind of sketch this, okay, what the z-score does is in the table it tells us, okay, here's 200. And if we figure out, if we go to the table, we can figure out, well, what's this area? And if we go to the table, we can also figure out what's this area? Okay? So there's an overlap, right? We don't want the overlap. We want just this. So what we could do is we take the cumulative area under 200 and we subtract it from the cumulative area under 320, and that will get us what's in the middle. Okay? So let's just make a note of that. The z-score table.
Everything that I have wanted in a child, I got.
He's my soul.
Gives us cumulative area below a certain number, specifically a z-score. So to find the area between two z-scores, subtract the area below the lower z-score. From the area below the higher z-score. So in other words, we're going to find the z-score for 200. Sorry, I don't know why I keep forgetting the c's. So we do 200 minus 305 over 40. And we actually did this. This was 2.63. Okay, we're going to go to our table and we're going to find the 2.63 again. So 2.63 was 0.9957. Sorry, this was negative 2.63. We're below. Okay, so we're going to go to the negatives. So negative 2.63 was 0.0043. Okay. So this is for below 200. Now we're going to do the same thing for 320. So to find the z-score, we do 320 minus 305 over 40. Get 0.375. If we round, that's 0.38. So we go to our table again. And again, be careful. We're in the positives. We're at 0.38. And remember, if you're above, your percentage should be greater than 50%. So it should be a number greater than 0.5. So just keep that in mind to make sure that you're not making mistakes. So we have to go to 0.38. 0.38 gives us 0.6480. So this is for below 320. Okay. So now we're going to get our answer, and to get our answer, we're going to do the second one minus the first, okay? .6480 minus 0.0043. That's going to be our answer. And we get 0.6437. That's our answer. So we take the larger minus the smaller. Okay, let's just do a little bit of work without having to worry about finding the z-score. I'm going to give you the z-score. Okay. So these are called cumulative areas. It's exactly what we've been doing. Okay, the only difference is that I'm giving you the z-score instead of you having to find it. Okay, so let's say below a z-score of 1.15. So if we go below a z-score of 1.15, we go to our z-score table. This is just some practice. We're above, it's a positive. So we go to 1.1, and then we go over to the 5, and we get 0.8729. And we're saying that's the percentage data that's going to fall below that z-score, okay? And here, it doesn't matter. When we say it's the percent of data that falls below that z-score, we're saying it's the percent of data that's below 1.15 standard deviations above the mean, regardless of what that mean and standard deviation are. It's always the same. So we have been working with a mean of 305 and a standard deviation of 40. If we had been working with a mean of 20 and a standard deviation of 2, we would get the same answer if we were 1.15 standard deviations above the mean. Okay? Let's say that below a z-score of negative 0.24. Okay. So again, this is just going to our chart. Just be careful. We need to go to the negative. So it's negative 0.24. So it's 0.24. So we go to the 0.2 and then we go to the 4. It's 0.4090. Let's do above a z-score. I keep leaving out these C's. Of 2.19. So here, again, we go to our table and we're going to the positive. We go to 2.19. 2.19 is 0.9857, but we have to subtract from 1 because we want above. So it's going to be 1 minus 0.9857. If we do 1 minus 0.9857, we get 0.0143. And notice it's a very small percentage that falls more than 2 standard deviations above the mean, okay? Very small percentage. So we subtract from 1, because we want the area above. Okay, let's do one more like that. Let's say that we want above negative, well, above a z-score of negative 1.23. Okay. So again, we go to our z-score table. We want the negatives now. Okay, notice negatives. The highest it goes, it doesn't go past 0.55. Okay. 0.50. If we go to, see, 0.50 is the highest number. If we go to negative 1.23, well, here's the negative 1.2. Now we have to go over to the 3. It's 0.1093, but again, we have to subtract from 1. And remember, you're always going to get a number less than 1. So if you get a number greater than 1, you did something wrong. Okay, let's say, for example, that we do a couple within a range. Okay, so in the range, of z-scores 0.26 to 1.67. Okay, so now we're going to find the one for 0.26. And then we're going to find the one for 0.167. So we're given the z-scores already, so we don't have to worry about that. So we're going to go, we're a positive. So we're going to go to 0.26. Here's 0.2. If we go over to the 6, it's 0.6026. And the other one was 1.67. So here's 1.6. We're going to go over to the 7. And we get 0.9525. So all we have to do here is subtract. It's always the bigger minus the smaller. And this is saying 35% falls within this range. Okay, don't round these. You can round your z-scores to the nearest hundredth because that's what the table requires. But you shouldn't be rounding your answers. Let's do one more. Let's do it in the range of z-scores negative 0.68 to 1.31. So again, we're going to find in the table the area before negative 0.68 and the area before 1.31. So for negative 0.68, again, we go to our z-score. We have to go to the negatives first. Here's the 0.6. We go over to the 8. It's 0.2483. Remember, this starts at 0, so be careful. Make sure that you're looking at the actual column. So it's 0.2483. And then the other one for 1.31, we go up to the positive. So 1.3. So again, be careful here because it's easy to start counting at 1, but this is the one. Okay, look at the top. It's 0.9049. And then we just subtract these, and that'll give us the area that's in between, the percent of data that's in between. And if we do that, we just get 0.6566. And that's our answer there. So again, about 66% of the data falls within 0.68 standard deviations below the mean to 1.3 standard deviations above the mean. That's what this is telling us, okay? So essentially what we did is we talked about the normal curve. We turned it into a standard curve. Standard just means that we're labeling it by standard deviations. And then we will use the z-scores to find the percentage of data either below a certain score, above a certain score, or in between, okay, in a range.